All right, and welcome back. So we've got another lecture today on section 2.6. At the end of the last lecture on 2.3, I said we're going to skip a few sections, which is true. We're skipping sections 2.4 and 2.5 and getting right into 2.6. This is arguably one of the most important sections of the entire year. It seriously has been debated amongst the pre-calculus professors here. Its importance has been debated as the most important. It's so useful. It is so useful, and it really boils down a lot of what you do into very understandable compartments. Okay, so we work all the time with different kinds of functions, and what today's lecture will teach you is how a lot of these functions really belong in the same category. They all belong in the same family of things. And so understanding the basic one, how you can understand how from this, you can learn from this, how understanding that basic one helps you understand them all in that family. And so this is a really important section that sort of brings a lot of these pieces together and helps you shift between multiple things, multiple items within that same family. So I'll try my best here. Hopefully there's no errors. But we'll go ahead and get started. So the name of this section is Transformations of Functions. Transformations of Functions. And it starts right off the bat with discussing how you can shift or move shift is the technical word I would say here, how you can shift or move a function. Okay, so how do you move a function? How do you shift it? So we can think of some of our common ones, right? We can think of a line. Well, how do you move it up? Or how do you move it to the right? So I take this point and I move it over here, and then I move it here, and then I move it here. And it's going to look identical to shifting up, which for a line is not a surprise. But what about for a parabola? A parabola is this cup-like shape. Comes from the graph of an x squared variable. Well, how do you shift it up? What do you do to it to do that? Or how do you shift it left or right? So what do you do to the graph of this thing to just move it to the right a little bit or a lot of it? So these are the first topics that we're going to talk about. And as you can see from what I said before, what this is essentially doing, if you learn how to shift appropriately, or if you learn how to undo shifts, is if you take any graph of a function, like say a parabola, something over here, if you can sort of think about it as a shift of just your standard one, which is centered at 0, 0, and looks normal, if you can figure out that shift, then you don't need to worry about what this thing is, because it has the exact same properties as this one. So you can, in a way, once you learn these shifting transformations, you can quickly translate from one oddball graph to a standard graph and apply what you know of the standard graph to figure out the oddball one. So it's an easy way to go about solving lots of problems in just one way, right? Transform it to the standard one, transform it back. So let's look at some of these transformations. The first one is a vertical shift. Vertical shift obviously means moving up or down. Okay, there's no left or right happening here. It's just up or down. We're going to handle these piece by piece. So before I get into this, I think it's a good idea to remember that in our function notation, x is our input, right? But this whole thing, that's our output, right? If we plug in 1 to this function that I just wrote down, we get the number 2. This is 2. So the function symbol with parentheses and the input, whether it's a variable or not, you could think of that like a variable on itself or on its own, a. Oftentimes we use the variable y to represent that. But it doesn't matter what you label it as. What's important here is think of this whole f of x as a output. It's an output. Okay, and what is that output? So you take an x and you get some f of x. You get some height for it. So you plug in the x, you do whatever you need to with it, and you do the computation to get that height, which corresponds to a point, x, f of x. Okay? So how do you shift a function up or down? Well, how do we take this point and move it up or move it down? I don't think it's too difficult to see that in order to move something up or down, what we really are trying to say here is if we want to move it up, we just add a little bit of something to it. Right? We take the output that we got before and we just bump it up. We just add a little something to it. So we get this new point at the same input, but now we've got the old output bumped up a little bit. Right? This distance here is the amount that we bumped it up. And this is how you vertically shift any function. You just add or subtract a little bit from the output. So if I have this graph, let's say f of x equals, let's make this a little bit not trivial, x cubed. We maybe don't know exactly what that looks like, not yet. That's our first one. Let's take another function, g of x equals x cubed minus, 3. Well, g of x is a vertical shift of f. Right? Here's our function f of x. It's just x cubed. Well, here it is too. That's f of x. And what did we do to it? We subtracted 3. So to each output of f of x, we subtracted 3. Which means, if I were to graph these two things, it'd be actually pretty simple. If I can graph one of them, then I can very simply graph the other one. So here's f of x. I'll just give it to you. Looks like this. What does g look like? Well, that, but every point is dropped 3 points. So 1, 2, 3. Here we go. I'll try my best. and I'll graph it in another color. G of x looks like that. It's the exact same graph as best as I can do, but just lowered 3 points, 3 units. You can see that in the equation. G of x is equal to f of x, the whole thing, subtracted by, or reduced by 3. So g of x is just a vertical shift of f of x. In other words, what I know about f, I now know about g, right? Properties of f now apply to properties of g. Okay, so vertical shifts essentially are accomplished by just adding or subtracting any constant to the output of your original function. They're not too difficult to analyze. The next one is a horizontal shift. These ones are a little bit trickier. Horizontal is left or right. There's no up or down movement with this. Again, we'll handle these piece by piece. We've handled up and down movements. We're about to handle left or right movements. Together you can create diagonal movements. So how do you shift left or right? Well, I'm going to do this with an example. So this is, as best I can draw it, the graph of x squared. What if we wanted to take this and move it over, say, to x equal to 10? We wanted to take this whole thing and bump it over to where the vertex is at 10, and then it goes up, does the same stuff, but at 10, that's where we want it centered, not at 0. Well, how would we do that? So remember that we're trying to work with something that's just like this, a square. So our function is going to be a square of something. So we want something squared. What is that something going to be? Well, before, when we squared 0, let's think about this point here. When we squared 0, we got 0. Now what we want to do is we want to plug in 10. Right, here we plug in 0 and we get 0 squared. Here, when we plug in 10, we want to get the same thing. We want to plug that 10 in, do something to it, square it, and then get 0 out. Well, the way we can accomplish that is subtracting 10. The amount that we shifted it over. We plug in 10, we subtract 10, square it, and get 0, which gives us that first point here, 10, comma 0. We plugged in 10, we got a height of 0. Let's look at another point. See if we can analyze how to accomplish the same thing. Let's look at the point here at 1. 1. Right, when you square 1, you get 1. So this is a point on our graph of the left function. On the right, what are we looking at doing? We're looking at plugging in 11. Right, we go 1 to the right, so we're going to go 1 to the right here, and we want the same height to come out. We want the same height. We're only shifting it right. We're not shifting it up or down. We want the same height to come out. So what do we need to do to 11 so that when we square the result, we get just 1? Well, it should be obvious. We subtract 10 to get 1. Square it and get 1. Do you see what's happening here? No matter what pairing I choose, I could say, let's look at any point on the original graph, and you know, like -5. Well, that brings us up to 25. Well, that's 5 to the left of our center. So this would give us 5. And what do we need? We need a height of 25. So what do we do to 5 and then square it to get 25? Well, we could do nothing, right? Which might cause some issues. Or we could try what we've done for the other points. Subtract 10. Well, that definitely gives us -5 squared. In fact, that gives us -5 just like we had here, which is great. And we've got it. And this illustrates exactly what you do to obtain a horizontal shift of a function. To shift a function to the ... right, like we did before, you subtract from the input. That's it. So if we want to take this graph and we want to move it over some number c to the right, we want to shift the whole thing over, all we do is we take the function f, which is the original one, we take our input and we subtract that c, and that's it. We saw that up here. This x squared was shifted to the right when we did this, x minus 10. We subtracted 10 from the input, then we did what the function says on that new input. The function says to square it, so we subtract 10 and we square that. We adjust the input first, and then we carry out the function's rules. So to shift a function to the right, you subtract. That's always a little bit backwards for students. It's difficult to keep straight, it really is. But the way I always try to explain it is that when you're subtracting from the inputs, it's like you're shifting the whole x-axis. And a way to move a graph to the right is like moving the axis to the left. Does that make sense? If you want to move a graph to the right, here's some graph. Here's its x value down here. X is 0. If we want to move this graph to the right, we could accomplish that by taking the axis and moving it to the left so that this graph is now over here. Right? And so I think that's where the subtraction makes the most sense, is that we're shifting our x-axis. We're subtracting from it, making things in the x-axis smaller. So we're moving the axis to the left. And that has the effect, if we sort of recenter the whole graph, that has the effect of moving the graph to the right. Okay, so that's that. To shift a function to the right, you subtract. You could guess. To shift a function to the left, you add to the input. Okay? And that has the same explanation. Moving something to the left, the graph to the left, can be accomplished by moving the x-axis to the right. And I'm not going to do an example of that, but it's almost synonymous with what we just did. So with that, we now know how to sort of think about some really odd graphs. So we could look at something like this. F of x equals x minus 3 squared plus 5. So this looks strange, but this is the graph of x squared. looks exactly the same. It's the graph of x squared shifted up 5. Right, we see the function x squared. There's something being squared there. And then 5 is added to it. So it's the graph of x squared shifted up 5 and right 3. That's because of that. So we've got our original graph of x squared, which looks just like this. If we move that up 5 and to the right 3, 1, 2, 3, 1, 2, 3, 4, 5, we get our new graph. This base point is moved up here, and the graph looks exactly the same. It's just moved up and to the right. Okay? So this is actually a pretty powerful thing, right? If you can make a function look in form like a basic one that you know, then you can graph it very, very, very quickly. So this algebraic manipulation is of utmost importance. And now we can characterize all sorts of weird functions, right? This one doesn't look right away like an x squared, but it is. And graphing that is no harder than graphing the original one that we graphed, or that we've graphed before, x squared. With that, we'll do a lot of problems on that on Wednesday, on one of these Wednesdays, but not right now. So the next thing that we'll talk about is another kind of transformation. This is reflecting graphs. So when we take a graph, if we want to reflect it about the x-axis, we can accomplish that by, for every x value, there's a y value associated to that. We can accomplish the reflection across the x-axis by just reversing the sign of every height. So for each x, y, so for every point, plot the same x with the opposite of y. That's how you can reflect any graph, any function across the x-axis. You just replace the y height with the negative of it. And what that does is changes this y height to this y height, so this point is here. Changes this y height to this y height, so this point is here. And you just get this that was strange. You just get this little reflection, right? Every height is associated with the negative height now. I tried my best, but you're trying to maintain this distance here and this distance being the same. So this distance is the same as this distance. Okay? So that's one way to reflect a graph, is plug in an x, get the usual y. That gives you your graph of the original function. But if you plug in your x, get your y, and then negate it, and you plot that, you're going to plot the exact reflection of it across the x-axis. Reflection across the y-axis is very similar. So this is our y-axis. If we have any graph, maybe something like this is our new function f. If we want to reflect it across the y-axis, in a similar way, what we're going to do is we're going to we're going to look at this. If we take an x value, we usually get this y value, right? For this thing to be a reflection across the x-axis, it'd be great if negative x gave us the same height. A reflection maintains a distance between a reflection line and the original point. So we want to make sure that when we plug in this x distance and get that height, when we reflect it, we want to make sure this distance here is the same, but that distance needs to be x, but in the opposite direction. So we just negate it. So to plot the y-axis reflection, plot for each xy that you originally have the point negative x, y. So don't change the y coordinate, just change the x coordinate. That's how you can reflect graphs across the y-axis and across the x-axis. So here we go. This one would look a little bit like this. If I just replaced every x with a negative x, it would look exactly like that. What are some nice examples of this? Square root of x looks like this. 0, 0, 1, 1, 4, 2, right? Like these are easy numbers to take square roots of. So what about the square root of negative x? Plug in 0, we get 0, so square root of 0 is 0. I'll graph this one in red. 0, 0. We plug in 1. We get negative 1. Yikes, can't do that. So what do we need to do? We plug in negative 1. And that gives us the square root of positive 1, which is 1. We plug in 4. Ooh, can't do that. We need to plug in negative 4 so that we get the square root of positive 4, which of course gives us a height of 2. There you go. We change the sign of the x, and we get the reflection across the y-axis of the graph of square root of x. So this can be pretty helpful, right? If you want to look at certain kinds of functions as families of functions. Now we can boil down translations horizontally or vertically. We can boil translations of them down to some untranslated function. Additionally, we can look at now all pairs of reflected graphs, and we can boil them down into just your standard unreflected, untranslated graph. And if we understand the untranslated graph, the unreflected graph, then we know what we need to about the reflected or translated. But there's more. What about stretching? Your book calls it stretching and shrinking. And there's two categories to this. There's vertical, and then there's horizontal. And I'm not going to belabor this point too much, because I think this one, the vertical one, makes a lot of sense. So we will remember that a graph's output is represented by this, f of x. That's the output. If we want to stretch the output of a function's graph, what we need to do is we need to multiply it by some number. Remember, adding some number to the output shifts it up and down. But if you multiply the whole function by some number, you're going to stretch it or you're going to shrink it vertically. So it is stretched, so that means made taller, if a is bigger than 1. So if you take, oh, and I should say this I should say the absolute value. If A is negative, you do get a stretching, but you also get a reflection. So I'm going to say that A is positive here. Okay, for A greater than 0 gives vertical stretching if A is bigger than 1. You can think about, like, if A is 1, nothing happens. But if you multiply every output by a number bigger than 1, you're going to increase the size of things. It's no different than graphing x squared versus 2x squared. This one, for an input of 1, gives you an output of 1. The one on the right gives you an output of 2. It's twice as tall. Shrinking is accomplished when A is in between 0 and 1. If you think of those numbers, something less than 1, bigger than 0, if you think of those numbers as a percentage, you're taking every height of your original function and you're just taking 80% of it or 50% of it, whatever A is as a decimal. You're taking a fraction of the original height. So the graph's height is stretched if A is bigger than 1, or it's shrunk if it's between 0 and 1, if that multiplier is between 0 and 1. At 0, you smash it all the way to the x-axis. At 1, you get the original thing back. So I'm not going to belabor that too much. I think that makes some sense, some easy sense. Horizontal is an altogether different beast. So just like before with the vertical shifting and the horizontal shifting, remember vertical shifting was done by adding to the output, and horizontal shifting was done by adjusting the x value. You adjust the input first, and that shifts the graph left to right. With the vertical shrinking and stretching, you adjust the output. With the horizontal, we're going to adjust. It's a horizontal shrinking and stretching. We're going to adjust the input. And just like before, where things were sort of backwards in this regards, we subtracted from the input to move things to the right. We added to move things to the left. Just like before, things are sort of backwards here, I will say. They seem a little bit backwards. So horizontal stretching and shrinking is accomplished by multiplying the input by some constant. I'll use the letter C to be that constant, and I'm going to make sure that that is bigger than 0. We don't want to destroy everything. We don't want to flip the sign of it. That would give us a reflection, right? We want to just make sure that we've multiplied by some some positive number. And here's what happens. Here is what happens. If you multiply the inputs by some number C bigger than 1, then you can guess, I said things are backwards, the graph shrinks horizontally. It like accordions in, it compresses in. The graph shrinks horizontally, and there's a nice factor here by a factor of the reciprocal. So if I pick like a number 2, right, the number 2, and I have a graph of f of x, but I multiply the inputs by 2, and that'll take our original graph, which I'll graph like this. That takes our original graph, and it compresses it 2 times. So it's half as wide as it was before. Okay, it takes that red graph and it just compresses it all in 2 times. Okay, so what I'm trying to say is every input is half as big. So we took this and we halved it. We took this and we halved it. We compress it. All right. If we pick a number between 0 and 1, just like the vertical stretching, we're going to get something that is now in the opposite direction, is now growing, but it has to be between 0 and 1. We can't pick 0, we can't pick, well, if we pick 1, nothing changes, right? The graph stretches horizontally. And again, by a factor of the reciprocal of C. So if I take my graph, say something like this, like what I drew before, this is F. If I multiply by 1/3, that's a number between 0 and 1. That has the effect of stretching it by a factor of 3. So this x value now becomes 1, 2, 3 of those. This x value stays at 0. This x value becomes 1, 2, 3 of those. So the new graph is stretched horizontally 3 times. Okay. So just like the shifting left and right, it's kind of backwards, I think. A lot of students struggle with that. But again, when you adjust the input, remember you're adjusting the x-axis. So you're stretching or shrinking the x-axis. And if you view what happens to the graph through that lens, I think it's easier to see why the graph compresses or shrinks when you multiply by a big number, and why it stretches when you multiply by a small number. Because what you're doing is you're adjusting the x-axis itself. You're stretching and compressing it in the opposite direction of what you see happening, which is what causes, when you readjust it back, which is what causes that end result. Okay, now the last thing for this section is to talk about some common kinds of functions. So 2 common function types. Even and odd. This is the word that these are the words that we describe them with. Turns out that certain kinds of functions, when you do some of these transformations that we talked about, specifically the reflections across the x-axis, and then another one which we didn't talk about, which I'll get to in a second, we usually divide functions up into these 2 categories, and then others which are not either of these. These are just really common ones that have nice properties, and so here they are. So an even function. They have symmetry with respect to the y-axis. So let me explain that before you jump at me. Symmetry, what does that even mean? So before we talked about what happens when you reflected a function across the y-axis, right? You just plug in the same height but for the opposite x value. So for every x and for every negative x, you get the same height, y. This is an example of an even function, the one that I've drawn. If for every x, f of x equals f of negative x. Okay, if for every input, so I pick this x, I get this height y. If you get the exact same height when you plug in negative x, my graph is not quite drawn right here. If you get the exact same height, then you're dealing with an even function. This is what symmetry with respect to the y-axis means. You can reflect across the y-axis and your graph is not changed. So here's another example of an even function. If I reflect this across the y-axis, nothing changes. Nothing. The x here associates with this height right here. Well, so does this x, which just so happens to be negative x. If I look at this distance and this distance, they're exactly the same. This is a graph of x squared. I could graph actually any x to the 4th, x to the 6th, x to the 8th. These are all even functions. And the powers on those exponents, or the powers on those variables, tells you that. They're straight up even functions. Graphically, you're just looking to see, can you flip it across the y-axis and get the exact same thing? If yes, you've got an even function. If not, then it's not even. Algebraically, you need to test. I'll use this example. Algebraically, you need to test. Here's the rule for positive x. What does this turn into when I plug in negative x? Well, let's see. Negative x squared. Well, that's also x squared because the negatives cancel out. So what I get for f of x is the same as what I get for f of negative x. So it's even. This is how you test if the rule for a function is even when you don't have the graph. You just take the rule, you plug in negative x, and you simplify. If you get the exact same thing as your original rule, you got an even function. Otherwise, it's not even. It doesn't mean it's odd. It might not be odd. It might be odd, it might not be. So let's talk about odd functions. This is not something that we've talked about yet. Odd functions have the property that they are symmetric with respect to the origin. So that's how your book says it. I'm going to say it like this. When you rotate the graph 180 degrees about the origin, okay, so if I take this graph, I put a pin in the origin, and then I rotate everything around 180 degrees, I get this, I think. Yep, something just like that. If the graph of a function has this property that when you put a pin in the origin, you rotate it around, if you get the exact same graph out, that's an odd function. And algebraically, what happens here is if for every input f of negative x equals negative f of x, then we call it, the function is odd. We call it odd. Okay. So what are we saying here? We're saying the opposite height. Right? So I plug in an x, and I get f of x. So that's this description right here that I just circled. We plug in an x and we get an f of x. If the opposite of that, so we take this height and we take the opposite of it. So this is negative f of x. If that height is the same as what we get when we plug in negative x, my graph is not quite drawn right. It should be about there. If we get the exact same height, then we've got ourselves an odd function. So this is a way to test not just the graph, this is a way to test the algebraic forms. So let me give you the basic example that's usually used. F of x equal to x cubed. This is our original function. Is it odd? Well, we're going to guess yes. But how do we test that? We do that. We plug in negative x. So this is negative x cubed. That is negative x times negative x times negative x. Well, two of these signs cancel out, and then there's one left over. So this is negative x cubed. That is equal to the opposite of our original function. F of negative x equals negative f of x. So we have here an odd function. That's the test. That's the algebraic test. And it's fortunate, it's the same test for both odd and even functions. You plug in negative x to the function. You simplify. If you get the original function back, then you've got an even function. So you plug in negative x. If you get ... simplify equals f of x even. If you can simplify it, you get the original function back, you got an even function. You plug in negative x equals ... you're simplifying. If you get the opposite of your original function, it's odd. It's very possible that you don't get either. So in that case, it's neither odd nor even. It's neither odd nor even, which is entirely possible. There are lots of functions which are neither odd or even. Okay? That's a longer lecture, but this is a lot of stuff, and so I wanted to include more. I wanted to include some more examples and give some bigger descriptions of what these things are. Talked about a lot of symmetries, a lot of reflections and translations. We talked about a lot about horizontally and vertically stretching and shrinking your graphs. We talked about determining if a function was even or odd here at the end, and all of this is just to try and boil down all these different functions that we've seen in problems into categories. We're going to try and distill them into specific categories, and these categories are translations of these standard examples. X squared, x cubed, square root x. These are like the standard functions, which we can then translate and move all about the plane. We can shrink them, we can stretch them, we can do all sorts of things to them. And all we're doing is we're adjusting the original standard example. So we've got all these families of functions now, and they've all been distilled down. And some of them have these really nice properties of evenness and oddness, which will come into play from time to time. So this is an important time to see that, and a good time to introduce it. So I hope that helps with your homework. If not, you'll just have to shoot me some emails. I know this set of questions can be difficult, so don't hesitate to ask, don't hesitate to reach out, and I'll see you next time.